So for today's session, we're gonna talk about transformations of functions. Um, Basically, in the last session, we talked about functions and how it is, like the definitions of functions and the requirements for a function. And now we're going into the transformations of functions. So there are three kinds of transformations in functions, which is the translations, the stretches, and the reflections. The first one would be translation. So if you have a function like this, and let's just say the function is 2x plus 3, then we add a minus a. So the function becomes 2x minus a plus 3. Then the function, let's just say if we draw in a graph, the function would originally look like something like this, with the y-intercept at 3. However, with the addition of minus a, it gets shifted. It gets shifted horizontally. And the change of the shift, so this would be, the change of shift would be denoted by A, is the horizontal shift. Then if the function experiences a change of like fx plus b, then it would shift upwards. So it would come like this. So from this point, it would go into this point. Well, for this one, it would be from this point, goes into this point.
I have a question.
Okay.
So how do you identify in case it's a longer equation than this? So how do you identify minus a and a and b if it's a or if it's b?
Mm,
So like if you
yeah.
say a is 2 in this case, and you open it up and you say 2x plus 7. Sorry, yeah,
So
2x minus 1. So will that be the same?
2x minus 1.
Yeah,
Let's just say there's another function like this.
yeah. And and taking a as 2.
Taking a as 2. So a equals to 2, something like that.
Yeah.
And then you insert like g x minus 2.
No, no, not like that. Not like that. In
Oh,
fx minus a, putting 2 over there, would it be the same as gx then?
okay, okay. So you insert, so in this, you insert a as 2. Insert it
Yeah.
here, and then you insert it here. Okay, so 2x minus, so a becomes 2. So it becomes like this, plus 3.
Yeah.
So if you multiply, it becomes, yeah, it becomes 2x minus 1. Yeah, you're correct about that. Yeah, so it can be, for example, if the a is equals to 2, it can be rewritten from this formula into this equation. The same goes for plus b. So essentially, this is, the b is for the vertical shifts. And it also applies in like, it actually also applies in general equations like these. Like if you see it's 2x minus 1, that means that the point here, the y-intercept is -1. If you like add 5, then it shifts up 5 coordinates, 5 ways. And this shift, if you want to write it in terms of vectors, it can also be written as A and B, seeing its vertical and horizontal shifts. So usually you use the vector translations when you have like a particular coordinate. Let's just say we have coordinate in here, we have coordinate x comma y, and it experiences a shift of fx minus a plus b. So you can multiply x y by ab, and it should give you the translate. I mean, technically, it should be written as like this: x y plus a b equals to a plus x and y b plus y. So this is your new vector, which can be turned into a plus x, comma b plus y. So this is going to be your new coordinate. Okay. So after translations, we have stretches. And like shifts, like the horizontal and vertical shifts we just had, we also have vertical and horizontal stretches. So let's take the example of a quadratic equation like this. If you have, let's just say we have, no, to make it more easily, let's just say we have y equals x squared. And if you multiply the function by a, so y equals to ax squared, it would experience what you call as a vertical stretch. So this particular function would become more narrower depending on like the value of a that you have. Or it can also become like less steep if the value of a is less than 1. And then you also have horizontal stretches, in which happens when you insert the value function inside of it. So for this one, we insert it outside of it. So if you have like a times x and fx is equals to x squared, then this would be ax squared. But then for this one, it would be ax squared. So it becomes a squared x squared. Okay, so for this, you would have horizontal stretches, which is in forms of flat. How do you? Sorry. Sorry. Well, I don't know how it's. Okay, so I'm not sure how the horizontal stretch would exactly look like in this form, because it will probably like be pretty similar to like the stretches of the vertical. But if you have something like this graph, the cubic graph, then the vertical stretch would look like something like this. So this one becomes like it stretches vertically, while the horizontal stretch would make the graph look something like small. Vertical, it would make the graph look flatter, like this. So basically, the one that would like kind of stay consistent for the vertical stretches would be the x values, while the y is going to be stretched. But for the horizontal stretch, the one that's going to be consistent would be the y values. The x values are going to be the ones that are stretched.
I didn't understand the vertical stretch one. Like, what's the general formula for it?
So for like a cubic or polynomial function, the formula of it would be something like ax to the power of 3 plus bx squared plus cx plus d. And if you have the like
So for the
horizontal.
vertical stretch, what do we do in this?
Sorry, can you rephrase that?
I said for the vertical stretch, what will you do in this?
Oh, okay. So for like the vertical stretch to happen, you mean?
Yeah.
Okay. So if we have, let's just say we have something like this graph.
Graphically, I understood. I'm just asking about the equation. Like, how will the equation change?
Like if we have, okay, um, x to the power of 3 plus 2x plus 1. Let's just say something like this. And then you want to do, let's just say this is the function. And then you want to do like a stretch here, right? Times p.
The vertical
So
stretch. Yeah.
so let's just say p is equals to 3. So
Okay.
that means that for p times fx, that would be 3 times fx, or 3 times x to the power of 3 plus 2x plus 1, which would equal to 3x to the power of 3 plus 6x plus 3. And it would
Mm-hmm.
like it would look like something like this.
Okay.
And then if you want the horizontal stretch, for example, with the same formula right here, for example, you want to qx, let's just have the value of 2. So you want, who's adding hearts? Amazing. Let's just say qx like this. Then that would be f 3x equals to 3x to the power of 3 plus 2, 3x plus 1. So that would, um, don't forget, if you have like something like this, then you have to multiply it one by one, since this is one variable and this is another
Is
variable.
that horizontal stretch?
Hmm?
F of qx is horizontal stretch or vertical stretch?
This is horizontal.
Okay.
So doing this would get you fx to the power of 3 plus 6x plus 1. And that would give you stretch like maybe something like this-ish. More flatter. No, like Yeah, like more compressed. Okay. Okay, so next up we have reflections. For reflections, if you have minus fx, that would be the x-axis reflection. So if we have something like, x plus 2, okay, if we have something fx equals to x plus 2, and then you want to add minus here, so it becomes minus x plus 2, which turns into minus x minus 2. The graph, which originally looks like this, would turn into a reflection in the x-axis. And then for the y-axis reflection, that would be f minus x, which becomes minus x plus 2, so it becomes minus x plus 2. So that would be somewhere here. This is the y-axis reflection. This is the x-axis reflection. Who was that? Okay, so I hope this is, this is pretty self-explanatory if you draw it. And then next up, we have miscellaneous translations, which I have no idea what they're talking on. Because when I check the book, they just say like, oh, the book gives you like a set of booklet, which tells you like some of the properties of these. So I have no idea what it is, so we can just skip that. And then last but not least, we have the graph of the reciprocal, which is y equals to 1 over fx quotient x. So there are some interesting properties that comes with this particular reciprocal. Okay, so let's just say if we have fx as x, then one of fx would be, well, technically 1 over x. So let's just say, yeah, since this is denoted by this, then this would be the graph of fx. And then the graph of 1 over x would be something like this. Okay. So what's going on in this graph is that if you have fx, the function of x as 0, in this case it's this point, this is 0, then the vertical, then for 1 over fx, it would be its vertical asymptote. As you can see, in this case, it is the vertical asymptote indeed, because when you have 1 over fx, it is approaching either infinity or minus infinity of the 0 point, but it's not touching it. The right term of it, I think, would be that it is tending to infinity. So as x tends to 0, it tends to infinity from the right, while as x tends to 0 from the left, it tends to minus infinity. And it goes like opposite ways, vice versa. You see, as the reciprocal graph tends to 0, either the left or right side, the fx graph starts to reach infinity, or it doesn't, well, technically it doesn't like literally reach it, but it doesn't like, it is undefined as you like go further and further. Um, and then for the local maxima and local minima, it's also this. That's also kind of like saying how um, the max the maximums of the fx, like when the fx is reaching like its local maximum or its local minimum, then for the reciprocal it's reaching its local minimum. I don't think you can really, okay, so I think it would be addressed better when you have like graphs like the quadratics. So if you have like fx squared and 1 over x squared, then like the drawing of the 1 over x squared would be, this is the local maximum, then the local, if this is the local minimum for this, then the local maximum would be, well, I'm not sure about the actual drawing, but it would be like one of the local minimums. Maybe it's something like this-ish, or maybe like this-ish kind of drawing. I personally have like, I've never drawn the reciprocal of like this graph, but if you really want to play around, I would definitely suggest playing around in Desmos. And then for its next function, basically it says that if fx is more than 0, then the reciprocal function would also be more than 0. So if it's like, and if it's less than 0, it also, the reciprocal is also less than 0. So anything other than like it's 0 has its, anything other than like the 0 value in the x-axis has a value for both of them. And then the last property that we have for today, which would be that when fx tends to 0, the reciprocal of it tends to infinity, either plus or minus. And this is basically like a reflection of this property of it. So that's pretty much it for today's session. We can do some questions if you like, or if you guys have any questions, I'll try my best to answer it.